In this part of the lesson, we are going to discuss the chain rule. To get a sense of this, I would like us to just find some partial derivatives here, and it will translate nicely into understanding of the chain rule. Okay, let's find par z par x. So that means first I need to find the derivative of this first term with respect to x. So I bring down the 3, and then we have x squared plus y squared to the power of 2. 3 stuff to the power of 2, and then the derivative of stuff with respect to x is simply 2x. Plus, now we're going to do the derivative of this term, which is bring down the 2, 5xy to the power of 1 times the derivative of stuff, and here the derivative of stuff is simply 5y. That should be straightforward review for you. Let's leave a little space here, and then we're going to find par z par y. And we have the same deal. 3 stuff to the power of 2 times the derivative of stuff with respect to y plus 2 stuff to the power of 1 times the derivative of stuff with respect to y. So the chain rule applies when you have composite functions. Here you could say in this portion here that we have a function within a function. So sometimes we make up function names to describe function within a function. Okay, so what do I mean by that? Let's come down here again, leaving a little space. Take the same example you have above, and instead let's introduce other function variables. Let's say z is equal to m cubed plus n squared. Now I just fabricated the m and the n. So in this case, m, if we're using the example above, is x squared plus y squared, and the n is equal to 5xy. So if I'm finding par z par x, as we already did above, well then we're going to pass through m, and we're also going to pass through n to get there. So what do I mean by that? We'll take the partial derivative of z with respect to m, so 3m squared, and then we take the partial derivative of m with respect to x. But then we also have to add to that the partial derivative of z with respect to n times the partial derivative of n with respect to x. In a similar way, if we take the partial derivative of z with respect to y, then we have the partial derivative of z with respect to m, and then the partial derivative of m with respect to y, plus the partial derivative of z with respect to n times the partial derivative of n with respect to y. That's what we did above. Oftentimes we draw a tree diagram for these. So we say z is the function, and we kind of work through or pass through these fabricated m and n functions, but m is a function of x and y, and n is also a function of x and y. So we do the partial derivative of z with respect to m, and then the partial derivative of m with respect to x, but there's another way to get to x, so we have to pass through n to get to x also. And so this here is considered the chain rule partition for partial derivatives. And if I just come up above here, I can see that this portion here was the partial derivative of z with respect to m, and then we multiplied that by the partial derivative of m with respect to x. Here, this portion here, partial derivative of z with respect to n times partial derivative of n with respect to x. And we can do a similar layout here, but ending with the partial derivative with respect to y. Final note on this first illustration here, if we say that z was originally a function of x and y, then we can interchange z and f. So z is the function f. So anywhere here we have a z, we could have replaced with f. So this would be par f par x equals par f par m times par m par x, and plus par f par n par x. Let's choose a different function here. Z equals m squared n. It's a new function, but let's keep m and n the same, just so we see how this plays out. So m is x squared plus y squared again, and n is 5xy. Okay, same deal. Z has to pass through m and n to get to x and y, as we showed in the tree diagram. So I proposed here that this was going to be par z, par x was going to be par z, par m times par m, par x, plus par z, par n times par n, par x. I still have this plus here, even though the function z is not m squared plus anything. I want to show how that sort of works out. So let's do this par z, par x in this fashion. So the partial derivative of z with respect to m is simply 2mn, and then we multiply that by par m, par x, plus the partial derivative of z with respect to n is simply m squared, and then par n, par x. Okay, so par z, par x is equal to 2. Now m was this x squared plus y squared, n was the 5xy, and then par m, par x, if I look up here, par m, par x is simply 2x, plus, now m squared would be x squared plus y squared squared, and then par n, par x would be 5y. And that's another way we could approach the problem. Now, I don't propose that you make this harder on yourself. You simply could, in the beginning, write z is equal to x squared plus y squared squared times 5xy, and then find par z, par x in the traditional manner using product rule and chain rule. But I really want to emphasize the structural feeling of the chain rule and get you used to this notation as it becomes important in proofs or different theoretical problems. In this next problem, let's say that w is some big function of r and s, but then r is some function of p and q, and s is some other function of p and q. Ultimately, what this means to me, that w is a function of both p and q. So let's sort of break this down in the tree diagram. So we have the function w. Now, the function w breaks into r and s, and then the function r breaks down to p and q, and the function s breaks down to p and q also. In this illustration here, the r and the f are interchangeable. Simply r is f. It's a general function notation for saying that r is a function, and s is equal to g, so those two can be interchanged. And essentially here, w could be interchanged with big F, so keep that in mind. Sometimes we interchange those for our convenience, but w ultimately is a function of p and q. And then, to use that terminology, manufactured, I sort of manufactured r and manufactured s. See, I manufactured them here as a way to reach out to get p and q. We have to pass through them. So let's write the chain rule partition for this particular scenario. So now, if I wanted to find the partial derivative of w with respect to, let's say, p, so this bottom rung here gives us the variables of interest. So par w par p is going to be the partial derivative of w with respect to r times the partial derivative of r with respect to p. And then I have to add to that the partial derivative of w with respect to s times the partial derivative of s with respect to p. In a similar way, the partial derivative of w with respect to q is going to be the partial derivative of w with respect to r times par r par q plus par w par s times par s par q. If we did some interchanging here, we could say that par big F par p could be the partial derivative of big F with respect to little f times partial derivative of little f with respect to p plus the partial derivative of big F with respect to g times the partial derivative of g with respect to p, and a similar thing could be done below, interchanging some of the variable names. Okay, our fourth illustration here. W is a function of x, y, and z, but we're going to note here that x is a function of t and only t. We're also going to say that y is a function of t and only t. And lastly, we're going to say that z is some function of t and only t. Hence, w is a function of t and t alone. So the bottom rung of a tree diagram would simply be t. So we have the function w that can be broken into x, y, and z, and I hope you see some of the interchangeability we could use here. But ultimately, x is a function of t, y is a function of t, and z is a function of t. Let's do the chain rule breakdown for this. So the partial derivative of w with respect to t is going to be, well, perhaps you can work ahead and have this down. It's really kind of the important part. So this is going to be the partial derivative of w with respect to x times the partial derivative of x with respect to t plus the partial derivative of w with respect to y times partial derivative of y with respect to t, finally plus partial derivative of w with respect to z times the partial derivative of z with respect to t. Hurrah! But I also want to point out here, if you will, that w is a function of t and t alone, so it would also be appropriate to say dw dt, direct derivatives, without needing the partial. Now, the partial derivative of w with respect to x is still needed because you could say or argue that we manufactured x, y, and z just to make our problem a little bit structurally different, but then par x par t could be written as dx dt instead of par x par t. And I chose to write it this way because I can. So let's continue on here. This is going to be plus par w par y times dy dt plus par w par z times dz dt. We could have said from the very get-go that par w par t is equal to dw dt in the event that we just bypass the x, y, and z altogether. But if we introduce the x, y, and z as a part of our chain linking function, then I do need to express dw dt using the chain rule partition, as I've just underlined here. Do you remember from a previous math class where you were given a relationship such as the one you see here, and then ultimately you were asked to find dy dx, the slope of a tangent to that curve? If you were in my course, I called that an amoeba. I called this an amoeba relationship, and we found dy dx, which was the tangent to the amoeba. Of course, in this scenario, y was a function of x, and we treated it accordingly. Now, we're going to find dy dx, that same thing, but we're going to use partial derivatives to do this. Okay, first off, I would like you to recognize that this left-hand side of the equation could be thought of as a function of two variables, f of xy equals 8. Then if I wrote f of xy and then I brought 8 over to the left-hand side, then I would have that function minus 8 equals 0, which then leads this to be yet another function. I'll call it big F of xy equals 0. Okay, now, if I let w equal any function big F of xy, that equals 0. And here I could say x is x and y is some function of x. Then I can use the chain rule here. If you think of w as broken into x and y, but then x is x and then y is a function of x. That's how I'm going to break down my partition. So I'm going to say par w par x is equal to par w par x times par x par x. I could also say dx over dx because x is a function of x, plus par w par y times the partial derivative of y with respect to x, or we could also just say dy dx because y is a function of x and x alone. Now, the partial derivative of w with respect to x equals the chain rule breakdown, which then also equals 0. Next, I'm going to rewrite this interchanging variables. So I'm going to say par f par x times 1 plus par f par y times dy dx equals 0. Now I'm going to take this equation and I'm going to solve it for dy dx. This is ultimately what I'm trying to do. Dy dx equals the negative of par f par x over par f par y, or said differently, negative f little x f little y, the notation for partial derivatives. If we go back to the original amoeba and we write big F of xy equals x squared y plus 5xy cubed minus x minus 8, and then the partial derivative of that f with respect to x is going to be 2xy plus 5y cubed minus 1, and the partial derivative of that f with respect to y is going to be x squared plus 15xy squared. So our dy dx, the thing we're trying to find, is going to be negative 2xy plus 5y cubed minus 1 over x squared plus 15xy squared. Now, for fun, if you wanted to, you can go back and do implicit differentiation and check that we get this same answer. Finally, I want to point out that you can use this equation that dy dx equals the negative of partial derivative with respect to x over partial derivative with respect to y. You can use that in our proof of why a gradient at point P is always orthogonal to the level curve at point P.